Poisson regression. So first of all, we have these two words, Poisson regression and log linear model. So to some extent, we already talked about a log linear model, right, when we went through all the different models in what we called log linear model notation, like x, y, jointly independent of z, or x, y, y, z, conditional independence model, and so on. And we talked, when we were presenting the sort of multinomial idea about these, we mentioned that you could factor a log linear model that had a Poisson response, or it was a Poisson model for count, Poisson sampling, into a one Poisson for the global, and then a multinomial, and we mostly focus on the multinomial. So Poisson regression and log linear model are kind of the same thing. The difference is that when everything is categorical, so like all the predictors, in other words, the definitions of cells. So all the predictors are categorical, and response is count, cell count. Then we typically call it a log linear model when some of the predictors are allowed to be continuous, and we want the response to be either a count allow some predictors continuous, allow, in other words, not necessarily allow the response to be a rate. And we would typically call it a Poisson regression. So we're assuming that y is Poisson with some mu, and we have some set 1 through n of cases or patterns in the multinomial pure contingency table setting. These cases or pattern corresponds to the cell in the table, and the count would be the number that we see in that cell. But for this thing, allowing a response to be a rate, we want to also allow for this situation where there's kind of one special predictor. And what do we mean by one special predictor? We mean, well, there's one predictor about which we're willing to assume a strong structured relationship, right? So we sort of know ahead of time what the beta is. And that's when this predictor is something like time or space. And what we want to think about is not the counts, mu I, but the counts divided by this variable rate. Right, so we want to correct the counts that we see, which would give us a totally different answer without that correction, with this additional information, which was how many hours or how many miles or whatever did we observe. So there are different sort of families of the same model, but they're all the same thing. So we call this as a GLM. So we have a link function. We have the parameter that we're interested in estimating, and the link function and of the parameter that we're interested in estimating is a function of some vector of predictors dot producted with a vector of betas or parameters, and we assume that y is Poisson, the response. And we might think of it as being Poisson in terms of the counts or in terms of a rate if we want to correct for these times. This part is the systematic component, or the linear predictor. So when we're doing diagnostics and we want to graph residuals against a linear predictor, it's always this part that we're the result of the linear function that we're using as the linear predictor. And then there's two link functions that appear in Poisson models. There's the log link. So that's the assumption that the log link is equal to the linear predictor. And of course, that makes somehow better sense because we don't want the parameter to be ever negative, but sometimes there's an identity link. And of course, the identity link couldn't possibly be true everywhere, but it certainly can be true or closer to true in some region of interest. Of course, the variance is equal to the mean in the case of a Poisson. And when you do such a Poisson regression for some real data, you'll often find that overdispersion happens because of some missed variable. The rate is changing, or a very common reason is that this is not capturing all the exposure factors. And when we have overdispersion, we add sort of a slack parameter or scale parameter, sigma, and we estimate this sail parameter. Or we can just change the model, negative binomial. I'm not sure that I'll talk about that explicitly, but there's another model called a negative binomial model, which is assuming a different distribution, which is a lot like the Poisson, except that it has more variance. So that would be changing our family. The link function might stay the same, but the meaning on the right-hand side is different. And in terms of thinking about what the parameters do, so suppose I have a log link function, and I say that the mean, some mean that I'm interested in, is equal to an intercept plus beta times some variable that's interesting to me. So in other words, mu is alpha plus beta x. So the x of alpha is the mean when x is 0, and x of beta is how much we multiply this mean. With a 1 unit increase in x. And to say that beta is 0 means we multiply by 1. And so the response and the variable are not related to each other. If beta is greater than 0, then the effect is positive. It's less than 0, the effect is negative. So then for this rate situation, let's think about what to do. So what we want to do is change from thinking about the counts to thinking about the rate. So we're modeling the expected value of yi over ti, and typically each observation, well, it varies, right? So sometimes each sort of cell will have its own t, or exposure, depending on how we constructed the experiment, and sometimes each observation will have its own t. Right? So if we have a data set where we have hours or something that goes down to the level of individual observations, we'll get that. So what we're saying is we think that this thing is some ui over ti, and log ui over ti has this linear form. Or log ui is log ti plus xi transpose beta. So this thing is this offset, because essentially we're just using the ordinary predictors, and we're assuming a very specific functional form for this predictor, which is that it just moves, it offsets the prediction from all the others on a log scale.
Yeah. I was wondering, where is the constant term, alpha? So alpha is cancel out. Whereas, I was wondering, just for function, we have alpha constant in the model, but somehow in the end we do not have the alpha. Whether
So alpha is like an intercept parameter. So when, say this was the two possible states, that is either state 0 or state 1. When it was state 0,
yes.
if I didn't have an alpha there, it would always make the same prediction. Right, so this allows us to make different predictions even in state 0.
Okay.
Change the rate.
Yes, so, sorry, one more quick question. I was wondering, for the Poisson case, I thought that the variance should be equal to the expectation.
Yeah, that's right. That's what
Why
we've
is
written.
the-
That's what we've written here.
Right.
So if we have over dispersion, so if that doesn't seem to be true from the data, then we allow there to be another parameter,
So
sigma.
the sigma squares from the, how can we just, to predict to estimate the sigma square? So that's
Right. So we'll talk about it a little bit later today, but usually it's that you just divide the observed chi-squared divided by the degrees of freedom. So, and that's our estimator. Yes?
Do you use the offset when there's a trend in your data?
When there's a trend.
When would you use the offset?
Let me get to the. So it's not when there's a trend. It's when every point in your data set. So let's say, like, if you think back to this example that I had before of airlines, where we're trying to decide which airline was more dangerous to fly on. And we counted, if instead of counting sort of absolute number of crashes or something, or rate of crash, what we counted was, we had a data set which was like maybe by route or something. And we had number of crashes per route. And then that information is sort of useful, but what would be better is if we had a rate parameter, like a t in there, which would be something like per seat miles, or per passenger miles or something, or number of times the right? Because what if one airline only runs that route once a week, and the other one runs it 1,000 times a week, and the 1,000 times a week, 1,000 times a week has more crashes than the one times a week. It doesn't necessarily mean it's more dangerous.
You're adjusting for another frequency or
Right.
another time parameter.
Right. We're adjusting for some kind of parameter that represents exposure, amount of time or amount of space, and it's special because we think of it as having a specific form. And one of the things that you can do you can test whether that was a good assumption by throwing that parameter in as a predictive parameter and seeing if the coefficient you get for it. So this sort of assumes the coefficient is 1 or negative 1, depending on what. Okay. So if you throw it in there and the coefficient is a lot different than 1, or doesn't seem to be sort of stably 1 across cases, then that's a sign that maybe that wasn't a great assumption. Right? But if it's close enough to 1, then it's probably reasonable. Okay. In other words, we're saying each of these mu i's for some case or observation is equal to this time parameter times what would otherwise be the prediction. Right, so we're multiplying this sort of underlying rate per unit time by the time that we've encountered the risk. And usually these MLEs will be obtained from software using something like the Newton-Raphson, or the or something like iteratively reweighted least squares, or some other optimization algorithm. So let's do an example. It's a classic example. It's a little bit long to write, but we'll put it here. So this is data from the 19th century by Władysław Bartkiewicz of fatalities in the Prussian army due to horse kicks. So this is, we have data of year and number of deaths, and it goes from 1875. In 1875, 3 people died due to horse kicks. In 76, there were 5. In 77, there were 7. In 78, there were 9. In 79, 10. In 80, there were 18. In 81, so that we don't have much in the way of predictors here, but this will illustrate a couple of other issues. 84, 9. Year, deaths. 1885, 5. 86, 11. 87, 15. 88, 6. 89, 11. 90, 17, 91, 12. 92, 15. 93, 8. And 94, 4. Okay, so that was the unfortunate gentlemen that were kicked by their horses. So we could look if there was a trend over time. That's one thing we could ask about that. We could fit an intercept-only model. That's sort of the null hypothesis. Right, this is it's not crazy to think about Poisson, because the number of times someone gets hit by a horse, some count that happens over the years. Okay, so intercept-only model. So how many degrees of freedom will the intercept-only model have? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 years in the data set. So what's the model degrees of freedom and the test degrees of freedom? I'm going to test for goodness of fit of that model.
Wouldn't the test be 19?
That's right. So the model has only one degree of freedom, which is the intercept, which is going to correspond to what number from these data sets, this data set? What number that you would compute from this? You could compute it not maybe by hand, well, you could do it by hand, but you could quickly do it with a calculator. There's one parameter, it's the intercept, right? It's the alpha. So I'm going to say, if alpha is the parameter, right, this is log linear model, so what is x alpha equal to? You could fit this one by hand. You don't need an optimization algorithm.
Just the average of all.
That's right. That's right. So it is in this case 8 is the average number of kicks or deaths per year. And so alpha is, and your software will agree with you, is 2.2824. And if you compute the deviance, or let's say the standard error, is 0.0714, and the deviance is 38 on 19 degrees of freedom. So the g squared divided by degrees of freedom, which is kind of your quick way of thinking about how good the model fits, is 2.0, say 2.03. So the model doesn't fit that well.
How do you know the fit by dividing the degrees of freedom of G squared?
Well, the degrees of freedom is equal to the expectation of the chi-squared statistic that we get out. Right? We had a chi-squared, the expectation of a chi-squared random variable. Well, let's say, okay, this is probably not quite right. X is chi-squared with d degrees of freedom. The expectation of x is equal to d. That's just a property of the chi-squared distribution. And so when the g squared that we observe is close to the degrees of freedom, that means the p-value is going to suggest that the model fits well. P-value will be large, right, close to 1. And when the g squared divided by the degrees of freedom is large, and 2 is pretty big, then the model fit will not be good, and the p-value will be smaller. Okay. So here we didn't fit any scale covariance, but we'll think about that in a second. So we have this lack of fit, right? This 2.0 just sort of says the fit is not great, and there's two reasons why it isn't great. One is that, well, we have another covariate that we could throw in, right? So far, we've completely ignored the fact that we know this is a time series, and we have like a predictor variable that goes from 1 to 20. So we could throw that in and hope that the g squared, as compared to the degrees of freedom, would go down. The fit would improve. And if that doesn't work, then perhaps we should throw in a over-dispersion parameter. Okay. So let's throw in year. So that's going to be sort of a continuous variable, 0 to 20. And what would if I ran that in some software, I would get out new deviance. So my degrees of freedom would be what now for the test? So this is with x2 equals year. And this is between 1 and 20 as a new variable. So we'll say something like death is year. And we have it fit with intercept. But you can think about that as being intercept plus year. Okay. So how many parameters, how many beta, or how many parameters are we fitting now?
2.
Yeah, 2, and there was 20 total, so now the degrees of freedom for the test will be 18. And the g squared turns out is 36.2, and the g squared divided by the degrees of freedom as a quick and dirty measure of fit is 2.01. Okay, so, fit hasn't improved a lot. The delta g squared is significant, but by this measure of just how well does the model fit, the fit is not really much better. And another way to say that is that when we look at the output, so we have an intercept, and we have a year. So we get the new estimates. So the estimate over here was 2.28. This estimate will now be 0.69. And the estimate for year will be 0.188. And the standard error for this one will be 1.06, and the standard error here will be 0.012. So neither of these is so great. And again, we don't have any scale. If you look at the residuals, you'll get something similar that says that, well, adding in year didn't really gain us much. So suppose we forget about that and we say, let's instead estimate a scale parameter. And we'll estimate it to be that. And that scale parameter here, because we're talking about exposure and we're seeing this variation, it could be that there was another parameter which was, say, size of the army. Right? There was the size of the army, and if that was my t, and I don't have that information, and so that's causing the overdispersion. And because it's not in the data set, there's nothing I can do about it. I've thrown in all the variables of the data set. The fit is still not good. I can tell myself at least a story about where the overdispersion might have come from, like army size, but I don't have that information, so I can't do anything. Okay, so what happens when I plug that in? Of course, the scaled, what will the scaled Pearson, so including the overdispersion parameter, the scaled Pearson chi-squared statistic for the fit will be what? So sorry, let me be clear. So I've thrown out, so no year. So this is an intercept only, 19 degrees of freedom in the test. But I also add in this scale parameter, which doesn't count against the degrees of freedom because it's sort of not part of the model. So I'll get a scaled deviance and a scaled Pearson. Can you tell me what scaled? So you know what scaled deviance, scaled Pearson is going to be.
So you're doing the scaled thing for the intercept only model first, and then.
Right. So I'm saying that okay, year didn't add much, so for now I'm going to throw it out and look at the intercept only model, but add in the scale parameter. If I ran this in RSAS, I would get out things like what is the Pearson, what is the deviance, which would be the same as the original intercept only model, and scaled Pearson and scaled deviance. So what will scaled Pearson be? What do you think? What's the formula for the scale parameter? That's going to be just 1. So basically, the scale parameter is chosen to make the scaled Pearson equal to 1. Think about it that way. This will be 1.0. And because we use this and not that, this won't be quite exactly 1.0, but it'll be pretty close. 0.276. And then if we look at our estimates of parameters, we have an intercept, and we have a scale. So our intercept has 1 degree of freedom. Our scale, we're not giving it any degrees of freedom. Probably some way of doing that, but I don't know how that works. We have an estimate, and the intercept will get exactly the same estimate that we got over here, which is it's just that value that makes the mean correct. And the scale parameter is going to be 1.404, and the standard error 0.1003. The standard error here is not really relevant because that's not how we estimated it. And so what changes as we compare it to the intercept-only model, the estimate of the parameter, the intercept, is exactly the same, but the standard error has increased. In order to, because of the introduction of the scale parameter, because of the introduction of the overdispersion. it's multiplied by this number, which is about root 2. Right? Because it's about the square root of this number that we've increased this standard deviation by. Okay, so now let's look at a case where we do have the data. So this was like there was a t, there was an offset lurking in here, which was maybe the size of the armory, but we didn't have access to it. So now let's look at a case where we do have access to it, and this is this example, which I think is in the online notes, which is the heart surgery example. So we have survival of patients after having their valves replaced, and it's sort of here's the table. So we have an age. They're either under 55 or over 55. And they have either aortic or mitral valves. We have a months with the valve, so that's our exposure parameter. And because of the way the data is collected, oftentimes we don't have any control over this type of thing, right? Or minimal control. Maybe we recruit patients to the study, but they have different. We try to get it as close as we can, but we can't make that perfect. And then we have deaths. 4, 1, 7, and 9. And if we think of this as just a 2x2 table, age versus valve type, and we just have these counts, it'll lead us to the wrong conclusion, potentially the wrong conclusion, because we haven't accounted for this months of exposure. How many months, total months, did the patients have the valve in? Right? Those who have the valves in more should expect to have a higher count. Right? So our model is that the number of deaths per cell, in this case, we have a total exposure of the entire cell as opposed to being on a patient level. So the number of deaths in cell I, we think is Poisson mu I, and mu I is equal to the exposure in cell I, the number of months, times some rate lambda I. So this thing is it has the interpretation now of the mean death rate per patient month. And so the hypothesis is that exposure is such that it's this number that we should relate to the covariates age and valve type, and not this number. We should assume a fixed function, a fixed form for the influence of exposure on that. But that's the form we've assumed. So using a log link, we have log mu I. Our linear predictor is, let's call it OI plus XI transpose beta, where this OI is the log of exposure, log number of months. And this thing is our offset. It's just added to the linear predictor. It becomes kind of an affine predictor. Well, there's an intercept in here. It's affine again. So this is a covariate whose coefficient is not estimated, but assumed to be 1. That's what we're doing implicitly, and we can then test later on whether we believe that that assumption is correct. So let's look at the saturated model. That the log of lambda is equal to beta naught intercept plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2, where we have dummy variables which codes 1 for under 55 and 0 for over 55, 55 or greater, and 1 for aortic, and 0 for mitral valve. So then we have death rates. Right, there's 4 cells. Each one has its own death rate, which gets multiplied by the exposure, log lambda 4. And these are just come from unpacking these. So this one would be beta naught plus beta 1 plus beta 2 plus beta 3, beta naught plus beta 1, beta naught plus beta 2, and beta naught. So this is the thing where both x's are 0. That is, it's over 55 and mitral. This would be over 55 and aortic. This would be mitral and under 55, and this would be aortic and under 55. So because this is saturated, we're again in the situation where we don't actually need to estimate these from the data. We can, or I mean, with using a computer, we can just calculate them because of this table, right? We have 4 unknowns, and we have 4 rates that we can compute by dividing. And so we can figure out what these are with a little linear algebra. So, right, beta naught is log L4, which is the rate here for mitral and 55 plus. Beta 1 is log lambda 2 minus log lambda 4. That's the effective age when type is mitral. Beta 2 is log lambda 3 minus log lambda 4. That's the effect of type when age is over 55. And then we have an interaction term. Which is the effective type when age is under 55 minus the effective type when age is over 55. And these numbers, these lambdas, we get directly from the data. So under the saturated model, our lambda 1 is just 4 divided by 1259. Our lambda 2, 3177. Our lambda 2, 1 over 2082, 0.00048. Lambda 3 is 7 over 1417. And lambda 4, 9 over 1647. And then we could take their logs to get these numbers. Minus 5.75, minus 7.64, minus 5.31, minus 5.21. And then we get these to be minus 5.2, minus 2.43, minus 0.101. Beta 3 is 1.99. Okay. So we can just read off directly all of the estimates under the saturated model, just like we can do that for, say, an independence model or a saturated model for some of the other examples we've been looking at. But one advantage of computing it with the software is that it will compute the standard errors, which are not as easy to get. And you could do that. And you would get something like this. So parameter, degrees of freedom, estimate, standard error. So let's see, the intercept we said was minus 5.2, and the standard error is 0.33. The under 55 the estimate is minus 2.4. The standard error is 1.05. The aortic dummy is 1, and degree of freedom minus 0.1 with standard error 0.5. And the interaction term has another degree of freedom 1.99 with standard error 1.22. Okay. So these two, the confidence interval will include 0, and these two they won't. So the main effect of age is significant. Because the model contains an interaction term, the main effect of age is actually the effect of age under 55 minus over 55 when the type is metral. And this minus 2.4 means that the death rate for the younger group is only about 2.43, 0.09, I would say 9% of the death rate for the older group when type is metral. So it's the effect of age is not significant. The main effect for type is not significant. The main effect for the interaction, or the effect for the interaction, is not quite significant, although almost there. Okay, so since this aortic one is not significant, we can test. We can do a hypothesis test to say, is aortic? Does the type have an effect or not? Is the type related to the death rate or not? So the reduced model for this test is that the log of the rate is just beta naught plus beta 1 x1. So we've lost the interaction and the type terms. So this has 2 degrees of freedom. We can fit it. And now you're going to need to use the software because it's not as straightforward as this. And let's see, we get beta naught estimated at minus 5.25 with standard error 0.25. That's a pretty good significance. And beta 1 hat to be minus 1.25 with a standard error of 0.51. Also pretty good. And you could get its fit statistics. So this deviance with 2 degrees of freedom, comparing it to the larger model because we've deleted 2 parameters versus the saturated model. The value is 3.78. So, this sort of rule of thumb, 1.89 is not too bad, I guess. Still not so great, but and the change in deviance 3.85 with 2 degrees of freedom. P-value is about 0.15. Okay, so we can sort of say that the model, the model fits. Doesn't fit very well, but it fits. I'm sorry. Yeah.
When we do the g squared divided by degrees of freedom,
Yeah.
1.89, what are we comparing that 1.89 to?
Yeah. I mean, so you should get the p-values. Look at the p-value. Look at the significance. I'm bringing it up today mainly is because it's a quick check. 2 is pretty close to is often around like where the cutoff is, but for significance in the usual sense. But yeah, it's just a quick check of fit. We expect it to be 1 if it's far off 1 and the sample size is big, then the significance it's going to be significantly bad fit. But yeah, the p-value is the main thing to look at.
Is that because the g square is approximate to the chi-square here?
Right.
So, okay.
Right. So that's the smart thing to do is to compute look at the chi-squared.
Because
Correct.
that's the over dispersion scale, but you also use the chi-square.
Right. And that's the number. This number is the one we force to 1 when we throw in an over dispersion. Well, not exactly this number, but the Pearson version of that number. Yeah.
What are we comparing this g squared to? Because we're getting a delta g squared of 3.85, which is bigger than 3.78, so it's obviously comparing to nothing.
Yeah, I think maybe yes. I think you're right. Okay. Because the other model is saturated, so it should have everything. Okay, so we implicitly still in this model, there's 1 parameter which we've fixed to be 1, which is the exposure parameter. Actually, that's why that's happening. I'm sorry, that's not right. It is that. I think the difference is the exposure parameter. That's why there's a missed fit even in the saturated model doesn't fit perfectly because of the exposure parameter. So, yeah. So if we want to test the exposure parameter itself, right? We've assumed it to be 1 structurally, but we could test that by throwing it into the model and seeing what happens. Of course, we can't throw it into the saturated model because we've already used up all of our degrees of freedom, but we can throw it into this reduced model, which still has some stuff left, and see what happens. So if we do that, so we say something like, this thing is age and offset, which is the log of the exposure, then we'll get out, we'll get out a intercept, an age parameter, intercept, age, and offset. And now we've given the offset a degree of freedom, and we get an estimate of 13 for the intercept, minus 1.14 for the age, and minus 1.54 for the offset, with a standard error of 1.6. So So what do we want to conclude from that? That I'm just confused for a second about the sign. If the negative is what we want or not what we want. I think it is what we want. So we think about 1.5 as being close to negative 1. And our delta G squared is going to be lower, but still not so good that that we could justify, or that, well, that not setting it to be equal to 1 is problematic.